So this is the start of the last unit, which really incorporates two smaller units, and the two smaller units are basically the way that we wrap everything together in terms of all the things that we learned throughout the course of the year of AP Chemistry. So the first thing we need to talk about is we need to go back and revisit thermodynamics and how to calculate them. And you may recall that there are the three laws of thermodynamics. The first one is the one that we spent a lot of time with that says energy cannot be created or destroyed, so the total amount of energy in the universe or the system happens to be constant. We also know that the internal energy of a system is equal to the sum of the kinetic energy plus the sum of the potential energy, and changes to energy occur through either heat and or work. So there's this generic formula for a change in energy, which is equal to Q, which is your heat, and W, which is work. We are going to spend a little bit of time talking about work later in a few days or in a few lectures, but for this one, we're just focus on heat. And so we may recall that H is enthalpy, and we can determine the enthalpy changes because we're talking about the internal energy, which is impossible to measure exactly. So we always talk about the fact that if there's energy at the beginning of the system, energy at the end of the system, we only care about the beginning and the end. We don't really care about the energy in the middle because that's really difficult for us to measure. So what we end up doing is calculating enthalpy, change in enthalpy of formation, and we use those values that are always given to us in a table or a chart, or we can calculate them, but we use those heat of or the enthalpy of formation values to calculate the change in enthalpy of the reaction. And so you might recall we did this once upon a time, that the change in the change in enthalpy of formation describes the formation of 1 mole. That's really important of a compound from its elements. So, for example, in the compound iodine monochloride, you have 1/2 of iodine plus 1/2, or 1/2 of elemental iodine plus 1/2 of elemental chlorine to produce the iodine monochloride. And so that would be the heat of formation reaction for that. And so the one thing that we can recall is that the heat of formation for something in its elemental or standard state is always 0. So something like I2 would be 0, and Cl2 would be 0. So in this case, we would use the formula that we talked about once upon a time that says the standard the standard change in enthalpy for the reaction is equal to the basically sum of the products minus the sum of reactants when we talk about their enthalpy of formation. And then the M and the N values in these calculations are always the coefficients from the balanced chemical equation. So to go through and kind of continue to review that, we did that math once before. We also used Hess's law, which you can manipulate a series of chemical reactions, each with their own change in enthalpy of reaction or their change in enthalpy of formation. You add them together to get the desired reaction, and we've done this before. So here we have methane breaking apart into carbon and hydrogen, and we have carbon and oxygen combining to make carbon dioxide, and then we have hydrogen and oxygen combining to make water, and we want to end up with our reaction for the combustion of methane, which would be methane plus oxygen makes carbon dioxide and water. So in this case, I would want to get rid of the carbon, not really get rid of it, but it sort of cancels itself out. I would also cancel out the hydrogen because on both sides of the equation, it appears and it cancels itself out. And so then at this point, I would go ahead and add these things together. And I would get the reactants, which is methane plus oxygen, and oxygen appears twice here and here, and makes 1 carbon dioxide and 2 waters, and so that's my balanced equation. So that we used Hess's law to do that. We knew that the change in enthalpy for the first reaction was positive 75 kilojoules per mole, and for the second reaction it was negative 394 kilojoules per mole, and the third reaction was negative 572 kilojoules per mole. So we added those things up and we got the combined reaction change in enthalpy of the reaction to be negative 891 kilojoules per mole. So, and because the delta H, or the enthalpy, is negative, this makes it an exothermic reaction. And moving forward, we also have one more way that we can calculate the change in enthalpy of reaction. We remember that the energy needed to break chemical bonds and is needed, and the energy is released when chemical bonds are formed. So we can take the change of enthalpy of a reaction, which would equal to the energy of bonds broken plus the energy of bonds released, or energy released when bonds are formed, and we use the bonds broken as positive values and the bonds formed as negative values. So in the example here, we have C2H5Cl plus chlorine makes C2H4Cl2 and HCl. In the reactant side, we have the bonds broken between carbon and carbon. There would be 5 carbon and hydrogen bonds, and there would be a carbon and chlorine bond, and then there would be a chlorine and chlorine bond as a reactant. So here are all that. And then as a product, we would have carbon-carbon. We would have 4 carbon hydrogens. We would have a carbon chlorine, and 2 of those actually end in hydrochloric acid. So these are those particular values. So then when I go through and I start adding things together, remember it's going to be bonds broken plus bonds formed. So I would take my 347 for the carbon-carbon. So I'm going to take the, let's see, bonds broken. So 347 for the carbon-carbon, the 414 for the carbon-hydrogen, and because there happens to be 5 of them, I would multiply that together. And then the 377 for the carbon-chlorine, and then the 243 for the chlorine-chlorine. And then I'm going to subtract that, and really what I should probably do here is put this all in parentheses, like that, and then this all in parentheses, like that. And then I'm going to start adding these things, or adding in the energy released. So in this case, we have 347 for the carbon-carbon. Oops. And we have 414 for the carbon-hydrogen times 4, and we have 377 for the carbon-chlorine times 2, and then we have 431 for the carbon and or the hydrogen and chlorine, and when we add them all together, we get a total value of negative 151 kilojoules per mole, and that would be the enthalpy of the reaction here. So that's the third way that we've calculated the enthalpy change in reaction. And then there's one more, and we use calorimetry data. And we use calorimetry data, we go back to using the formula Q is equal to mass times specific heat times change in temperature, and that will give us our value in joules, and then we'd have to convert that to kilojoules. So we use the idea that energy is released during a reaction is the same as the energy absorbed by the materials in the container. And as a result, the energy absorbed by the system has to be the same amount as the energy released by the system, so it maintains equilibrium. Now, to review some things about sign conventions, that is, whether something is positive or negative, in calorimetry, we have to remember that exothermic reactions, there is a temperature increase, and because temperature is being of the surroundings is being measured, and the bonds of the products are more stable or stronger than the bonds of the reactants. That's pretty important. So the bonds of the products are more stable than the bonds of the reactants. So the potential energy is lower. The extra potential energy is converted to thermal energy, which is released out of the system, and we measure that. And in endothermic reactions, we have a negative temperature change. And since in this case the bonds of the reactants are more stable or stronger in the bonds of the products, the potential energy needs to increase in the system, and as a result of that, the thermal energy from outside is converted into chemical potential energy, so the outside temperature decreases. So to go back to think about that in terms of a picture, in an exothermic reaction, we'd have a reaction that looks something like that, and in an endothermic reaction, we'd have a reaction that looks something like that. Okay, so where the temperature is being measured, or the energy is being measured, is beginning versus end. Another law of thermodynamics is Hess's law. And Hess's law, is the second law of thermodynamics, and that says the entropy of the universe is always increasing. And we haven't talked about entropy yet, so we're going to talk about that now. Entropy is basically defined as a measure of a number of different ways, W, which is a new W, we haven't talked about this yet, to arrange particles in a system with no change in internal energy. What that means is that the universe is constantly moving towards entropy. And entropy is an extensive property, and it always depends on the amount of substance. So if I have a little bit of substance A versus a lot of substance V, the entropy can be affected by that. So the more complex or difficult the molecule or the system is, the higher number of something called microstates. And each way that we arrange a particle or a system is called a microstate. And so we'll talk about that in a little bit different, in a little bit more complex or discussion in a second. So for example, C2H6, which is ethane, which looks something like this, versus methane, which looks something like this. There are more variations in ways to arrange ethane, C2H6, because it has more atoms, than methane, CH4. So as a result of that, it has more ethane has more microstates to begin with. Now, if we change temperatures, so if we say something like if ethane and methane are at the same temperature, then we would definitely say that ethane has more microstates, but if they're at different temperatures but the same compound, the greater temperature would have more microstates as well. So we'll come back to that. I've got a great picture coming up on that in a second. So the third law of thermodynamics says that entropy of a perfect crystal at absolute zero is always equal to zero. And then we have a new formula called S is equal to K natural log of W. So S is entropy, K is the Boltzmann constant, and W is the number of possible microstates. Boltzmann constant is something that you would never have to memorize, but it's 1.38 times 10 to the minus 23 joules per Kelvin. So if the number of microstates is 1, that is, there's only one possible microstate, then that would mean that entropy is equal to 0. But because of the way that we define entropy, every substance has some measurable entropy. So the change in enthalpy formation, if it's 0 for each of the elements listed below, cadmium, calcium, and bromine, the standard state of entropy is not going to be 0. So that would mean that for cadmium, if we would say that the change of formation here is equal to 0 for all of these going down, the change or the standard state of entropy would be 51.5, 41.6, and 152.23 respectively. Now, the entropy is always at the same conditions, that is 298 K, 1 atmosphere of pressure for a gas, and 1 molar concentration for things that are solutions. So, let's take a look at what microstates and vibrational motion actually mean. So as a molecule gets more and more complex, that is, we add more parts to it, it has more of ability to vibrate. So, and then if there's more vibration, there's more microstates of that actual substance, and as a result of that, that creates more entropy. So in NO, where it's just one nitrogen and one oxygen, the only way that it can vibrate is sort of squishing in together or pulling out. So it has some complexity, but not a lot compared to, say, NO2, where the nitrogen and oxygen on the right sides can squish in and pull out, and the nitrogen and oxygen on the left side can squish in and pull out, but then also the oxygen and the oxygen can kind of be attracted and repelled by one another and create a lot more opportunity for different, for lack of a better term, states of existence, hence the microstate. And then for N2O4, you can get squished. The atoms can be squished in or pulled out, but then the oxygens can also be vibrating up and down. So the deal is that entropy of elements tends to follow the same pattern. The more complex the element is, or the compound is, the more entropy the system is, the entity is going to have. And so that's really important to understand. So if I take something like ethanol, which is C2, ethanol, which is C2H3OH, something like that, and I go ahead and I dissolve it into water, what ends up happening is that there's going to be a increase in entropy, but not a lot. And the reason why there's not going to be a lot of increase in entropy is because even though I'm taking ethanol and I'm separating the intermolecular forces of attraction between ethanol, and I'm putting it into water and separating the intermolecular forces of attraction in between water and creating new forces of attraction for water and ethanol, both of them happen to be interacting via hydrogen bonds. So the individual motion of the actual particles is still restricted, and so as a result of that, the increase of entropy is relatively small. So one of the things that we want to talk about is if we mix stuff together, we tend to make entropy get bigger or increase, but the mixed system has, but in this case, the mixed system tends to have more disorder. That is, entropy, or that is the system itself becomes a little bit more complicated. So if you see ethanol's picture here, it seems to have some degree of organization or order. Water definitely has some degree of organization or order, but when you add ethanol into the water, that degree of organization is a little bit less, and that's what happens when entropy increases. Now, if we add salt to water, there is a huge increase in disorder because we are, one, separating the ions of the sodium and the chlorine in the case of table salt, and we're separating those forces of attraction, and then we are also separating the hydrogen bond forces of attraction. And when we put those things together, the water molecules are reorientating themselves so that they are really focusing around the positive sodium and the negative chloride ion, and as a result of that, they become more disordered. So the whole system tends to have a little bit more disorder, but the issue is that salt becomes more disordered because of dissociation, so there's an entropy increase. And then water becomes more ordered because now we have an ion dipole interaction, so we have an entropy decrease. So when you mix a salt with water in terms of dissolving, one thing has a higher degree or order, higher degree of entropy, and then the other thing becomes a little bit more ordered. So there's always that give and take, and it depends on what the problem or the question is asking you to take a look at. Another thing that's important to understand is that as you increase temperature of substances, the molecules are gaining energy, so they're moving more, their disorder is going to increase, and we're causing an increase in entropy. So anytime that we go from a solid to a liquid to a gas, there is an increase in entropy, but then the decrease in entropy would go the other direction. So if I take a solid and I add heat to it, it becomes a liquid. Those solid particles can have more motion, and because they have more motion, they are going to have more disorder, and so we're going to have the entropy go up. But if I take a gas, for example, and I take temperature away, the molecules are going to slow down, and as a result of them moving less, they're going to become more ordered, and the entropy is going to decrease. So that's something to kind of think about in terms of states of matter. There's also a huge entropy decrease when gas dissolves itself into a liquid. So, for example, if I take oxygen gas and I dump it into water and I make it dissolve, we have an entropy decrease in the oxygen. So the oxygen gas molecules are moving randomly around according to the kinetic molecular theory. When they get into the water, there's dipole interactions that occur between water and oxygen, and as a result of that, the oxygen molecules themselves become more ordered, so entropy decreases. Whereas if I take a soda or sparkling water and I open the cap on the bottle, you hear that fizzing. And that fizzing is because the process of carbon dioxide gas is coming out of solution, and it happens to be something called thermodynamically favored, which I'm going to talk about tomorrow. And so what happens is that the carbon dioxide is coming out of solution, so the dipole interactions between water and carbon dioxide are not strong enough when you open the bottle, and as a result of that, the carbon dioxide comes out and starts behaving more like a gas, and then according to the kinetic molecular theory, it moves around randomly, and as a result of that, there's an increase in entropy that for the carbon dioxide. So entropy, and that tends to drive this particular process. So the three ways that we can expect an entropy increase is when gases are formed from either solids or liquids, so changes of states of matter. Liquids or solutions form from solids, so another state of matter, or the number of gas molecules increases during a chemical reaction, which is kind of important. So as an example, we can predict the entropy change for each system as being positive or negative. So when I'm looking at system A, I have hydrogen and oxygen making water. So in this case, we are having two gases form a liquid. And as a result of that, because the gases become more ordered, so because the gases are becoming more ordered as a liquid, we would say that the change in entropy would be negative. Okay, so basically entropy decreases. In position B, or substance B, we have ammonium chloride as a solid, and it's breaking apart into ammonia gas and hydrogen chloride gas. So here we have a solid becomes less ordered as a gas. In this case, the change in entropy is going to be positive because entropy is increasing. It's becoming more disordered. Okay, and then we have a hydrogen gas and a bromine gas making a hydrogen bromide gas. And in this case, I would say that it is impossible to determine the sign of the change in entropy. Because in this case, I have 1 mole of reactant hydrogen and 1 mole of reactant bromine and 2 moles of reactant product, and they both happen to be gases, so I can't determine what happened to the actual number of gas molecules. So because there's 1 mole of each reactant and 2 moles of product, we cannot predict. Oh boy, that's no good. Cannot predict the sign of the change in entropy. So in this case, we would say that the change in entropy has to be close to 0. And it would be close to 0 because we are making the assumption that the number of gas molecules you start with are going to be equal to the number of gas molecules you end with because the equation is balanced as such. All right, so take a look at the problems for homework and just try them, and then I'll go give answer key shortly, and hopefully if you have any questions, shoot me an email, and we'll go from there. So have a good afternoon.